Okay, so in the last class we are looking at the finite difference method, and then we found out a way to express the first derivative using the forward differences, backward differences as well as central differences. The power of the central differences lies in the fact that a central difference results in a second order accurate scheme. Okay. Therefore, for a given grid size the order of the error insofar as the truncation error is concerned, the truncation error arises because you are replacing a derivative by only a finite number of terms in an infinite series. So, delta x squared by 2 factorial is much better than delta x, therefore the central difference is much more powerful. So, we applied the central differences to the problem of Laplace equation, and then we found out that for an equi-space grid the temperature at any node is just the algebraic sum of all the 4 is the weighted average of all the 4 neighboring nodes. So, the weights are 25% if delta x equal to delta y, the weights may be different from 25% if they are not equi-space. You remember in one of the earlier lectures I looked at the Lagrange interpolation scheme. So, Lagrange interpolating polynomial. So, you can use a second order Lagrange polynomial for x and second order Lagrange polynomial for y or third order, and then get d square t by dx square and d square t by dy square. You will again get Tij as a function of all the neighboring nodes, but here you will not get 25%, 25%, 25%, 25% depending on your grid. Suppose you first algebraically generate the grid using a cosine function or a tan function or a sin theta, cos theta, or using a geometric progression, then for a particular node we can take nodes ahead and behind, or 2 nodes ahead and 2 nodes behind, use a Lagrange interpolation and develop higher order schemes. So, with higher order schemes the advantage is with less number of grids you can get a solution which otherwise would involve a larger number of grids for a lower order scheme. So, for example, we considered only 4 points as a neighbor. You can consider one more point in the north, one more point in the east, one more point in the south, one more point in the west. So, that means you look at 8 neighbors for each of the points. So, that is called a 9 node stencil, or the last 4 could be like this, right. For this point, okay, for this point you consider 1, 2, 3, 4. Let us take, no, it is not very clear. For this point what you can do is you can consider 1, 2, 1, 2, 1, 2, 1, 2, or you can do 1, you can consider 1, 2, 3, 4. So, for this point all the corners can be considered. So that is what is called as a 9 point stencil. Now, let us take a simple problem, 2D steady state heat conduction. So, the slab is 10 centimeter by 10 centimeter, it is equi-space. For simplicity we are having only 4 points 1, 2, 3, 4, okay. So, we want to use the central difference formula to numerically solve this problem instead of using the series expansion, the series solution which we obtained in the last class, okay. So, T1, please note you can write the equation for T1 is 100 plus 0 plus T2 will be 100 plus 0 So, the question is solve using finite differences. So, T3 will be equal to neighbors north T1 plus 0 plus 0 plus T4. T4 is T2 plus T3 plus 0 plus 0. So, you put up a tabular column, serial number, okay. I will call the error as yeah, it is iteration number, or you do not like I, you put I plus 1 whatever. Oh, so J, R, so this will be Ti R plus 1 minus this is R plus 1th iteration minus rth iteration, okay. I will start with 20, 20, 20, 20 for all the 4, okay. I have not started iteration, so I cannot calculate error, I put dash because I have not started. Now I want to use Gauss-Seidel method. What is the Gauss-Seidel method? Now it will go in this sequence, okay. First I will use T2 and T3, with that I will get T1, wherever T1 comes I will use the latest value of T1, T4 is not done yet, I will use the old value of T4. Now after T2 is done, no, after T2 in this equation I can use only T1, but when I come to this equation I can use T2 and T3. I use the latest values or the updated values of the temperatures as the iterations proceed. I do not do all the things one at a time. For example, for all T1, T2, T4 I do not take 20. Once I calculate T1, latest value of T1 I will use, okay. So what is that? T1 will become
35,
okay, then T2 155 by 4,
38.75,
then
13.75,
error, yeah, you have to just take 35 minus 20 whole square plus 38.75 minus 20 whole square plus
662.9,
good 662 663. Everybody through with this? I have not given the problem number because I have lost track of the problem number, okay. Now T1, please use the latest values,
38.125,
we will say 38.1, T2,
yeah,
is it 12 point, is it correct? Just check.
37.03,
37.03, okay. Now
12.8125,
twelve point six 7, error has drastically come down, see. So we are using the Gauss-Seidel method, which I have already discussed, in this course, okay. So 11 point? Oh, see how much it has drastically reduced. Third iteration it will converge. 37 point? Okay, I will make it 7 then. 37.6. Huh? 12.6.
12.55.
12.6. Yeah, error.
Can be 12.6 and 12.6.
Yeah, it's okay. 3 and 4 are symmetric, na? Hmm.
Point 2.
Yeah, so we almost reached. So maybe this r squared, you can make it less than 0.01 or something. You want to do one more iteration? Shall we do? Just one more. You can see that it is rapidly converging. 37.6. Hmm. That is 1.5. Twelve point six. Yeah. 0.03. Okay. So we have come to we are very close to the true solution. So please remember that the central difference gives you only a numerical scheme. Then you get a set of resultant algebraic equations. We have used one more technique, which is the Gauss-Seidel method. Gauss-Seidel method is we are taking initial guess for all the values T1, T2, T3, T4. Right side is completely known, left side is unknown, the latest is substituted, and then iteratively we keep on solving till the error reduces. We can actually invert the matrix and solve for T1, T2, T3, T4 also, but beyond 100 by 100 it is very difficult to solve. It leads to a lot of errors and also memory problems and all that. Gauss-Seidel will work very well. Okay, the same Gauss-Seidel is also used in commercial software for solving the Navier-Stokes equations also. Okay, now you can see that 37.6, 37.5, 12.6, 12.5. Now common sense tells you that this center temperature must be 100 plus 0 plus 0 plus 0 by 4. The center temperature must be close to 25. Now we have got T1, T2, T3, T4. Please take the average of T1, T2, T3, T4 and see whether it is close to 25. No, 25.0. Very good. So the finite difference works. Okay, so you can make, if you see for 4 by 4 you can do with hand calculation. If you are making it 10 by 10, 20 by 20, 30 by 30, then you have to write a program. Gauss-Seidel is very easy to program. Do I equal to 1 to j, j equal to 1 to j. For do I equal to 1 to 20, j equal to 1 to 20, for all ij, t of ij is some t initial, then keep updating and then evaluate the criterion. If r squared is less than this thing, come out of the loop. If r squared is greater than, go back. I equal to I plus 1, j equal to j plus 1, that is the iteration counter, you can set it. Okay. So this is how the Gauss-Seidel method works. So now you have a good idea of how to solve a 2-dimensional conduction problem. in Cartesian coordinates, this can be extended to spherical and cylindrical coordinates. Even if I make a small change and add a heat generation, this T1 will be 100 plus 0 plus QV delta x square by k, that term will get added and you can solve and get the solution, right. Now we will see for a problem which is similar to this how we can apply the finite volume method, what the finite volume method is all about, then we will close our discussion on steady state problems, then how do we handle numerically the one dimensional transient and steady conduction, basic ideas, same finite difference. So how the delta t and delta x must be chosen such that you have a scheme which is numerically stable, with that we will close, okay. Now it is also called the control volume method. Also called the control volume method, okay. Here we do not use the Taylor series approximation, we will basically look at a flux balance, okay. Let us consider 2D okay. You take an area or a volume, this is called the finite volume or control volume. For purposes of illustration, I have taken a large control volume compared to the area size of the slab. So the slab is like this could be L and this could be W. L need not be equal to W, if L equal to W you have a square slab, it can be a rectangular slab also. This control volume is centered around the node P, node P is our node of interest. We want to find out the story of the temperature or velocity or whatever at the node P, okay. This node P has some neighbors, east, west, north and south. Oh I messed up, okay. Okay, it has 4 neighbors. To make the problem, to make it tractable, I will say this is delta x, this is also delta x. That is the distance between east and P is delta x, distance between P and west is also delta x, and north and P is delta x and south and P is delta x. I have exactly taken half of this distance, half and half, I have made a control volume. Now it is 2 dimensional steady constant property, I have to find out it is only conduction, no convection is taking place, no heat is generated, it is steady, no enthalpy is stored or depleted in the control volume. Now I have to apply the flux balance. This is just the starting point of our derivation of the governing equation. But then when you do that, k dt by dx, I put a Tp minus Tw by delta x, there I put an approximation, that is a control volume, that will be valid if the control volume is very small, okay. I can't put that k dt in a boundary layer, dt by dx is T2 minus T1, put a thermocouple outside the boundary layer, say T2 minus T1 by Y2 minus Y1. But if you are able to put thermocouple within this so that it does not affect the boundary layer, you are still getting reliable results, you can use that logic, because Q conduction will be equal to Q convection at the first layer. Now let us get back to this. Now flux balance, the control volume is infinitely deep in the direction perpendicular to the plane of the board, or you can assume it to be 1 meter, you can assume it to be 1 meter. Now here there is a conduction heat flux which is entering, here there is a conduction heat flux which is leaving, here there is a conduction heat flux entering, here there is a conduction heat flux. The net, the algebraic sum of all these fluxes will be 0 because there is nothing else in this problem. Let us start from the left, minus k Tp minus T west divided by delta x. When it is entering Q, when it enters a control volume, it is positive. When Q leaves a control volume, it is negative. That is the sign convention of thermodynamics. But W leaving a control volume is positive, W entering a control volume is negative. So we stick to this. Minus k is already is coming because of the Fourier's law of heat conduction into delta y into 1. Let us keep it delta y into 1. I will then say delta y equal to delta x, okay, so that you are clear. Plus k into T east minus Tp. Is this clear? This is the flux which is coming out of this. I put minus k dt by dx into minus because it is the flux which is coming out. The control volume is losing that flux. So it is a minus of minus, that is why it becomes plus. So this is east and west is accounted, north and south. When it is entering from the south, minus k Tp minus Ts by delta y into delta x into 1. The delta x delta y, you know why it is coming, right, plus the algebraic sum of all the fluxes equal to 0. If you want algebraic sum of all the fluxes plus whatever is generated, if you want generation, qv into delta x into delta y into 1 you can add. If it is not equal to 0, rho Cp into delta x into delta y into 1 into dou t by dou tau, whatever you want you keep on adding, that is all, okay. Now what is the equation number? We will continue from, or we will start with 1, okay. Now if you simplify, what do you get? Let delta x be equal to delta y. So I think it's cancelled. The answer is exactly the same as what you got using central differences. It should be the same, we can't get any other answer, okay. There is no approximation except that dt by dx we are approximating by this because it is an elemental control volume, it is okay. I do not want to put dt by dx equal to this, again Taylor series expansion is not required because I am using a small control volume. So long as the control volume is small, this will work, okay. So this is basically actually we should say it is a control volume based or finite volume based finite differences because I am using finite difference here. What the FEM people will do here is instead of taking dt by dx as Tp minus Tw by delta x, what they will do, T they will put it as T is equal to A plus Bx plus Cx square. Then they will get this ABC, and this ABC they got elemental coefficients, like that this ABC they will evaluate for all control volumes, they will assemble, it will be a matrix and they will solve it, and shape function of the element and all that they will do all that. So, this formulation for FEM also starts here, then they will start playing later on. They will not use the Taylor series, but here we are using the Taylor series. So, for a constant, if delta x equal to delta y and all that, after some time you do not know what is the difference, whether it is finite difference or finite volume. Okay. So, it is finite volume based finite differences, is that clear? So, you can, but this is more rigorous, but basically you do not start from some governing equation, all that. It is like as though you have got the governing equation. The governing equation basically will be differential form of this, you are actually working on the integral form of this. You approximate it for dt square by dx square, you do not use the dt square by dx square here, you are approximating only for dt by dx. Okay, are you able to see the similarities and differences between these? Okay, but if you don't like to put it like this and put it as a polynomial function or something, and then it becomes finite element, that is it. There is something called boundary element method, all that. This is a special class of techniques which have been developed. Okay, so with this we will close our discussion, but only one thing is the formulation I have given you is only for the interior nodes. You need to have a formulation for the boundary nodes also. Just 5 minutes we will see the formulation, how to do formulation for boundary node, and then we will go to unsteady and then close. So, this is east plus west plus north plus south by 4. Okay. If you have non-uniform grids, they call it 5. That weights can be immediately calculated once you finalize the grid size. Once you decide your grid, the weights can be calculated. For any ij you can calculate the grid, correct? For uniform grid size all the w's are 0.25, is that clear? So 1, 2, yeah, I dip. Okay, now is it okay? Yeah. Formulation for a boundary node. So, you are hitting a boundary here, that means you are having h and t infinity. Okay. So, you have your ij here. How do you think we can solve this? No, your ij is here. this P west, all are there except the east. East is gone. Okay. Now you can develop, have a half control volume. Okay. Okay. Q1, Q2, Q3, Q convection. Okay. So, is that correct? Q1 and Q2 are entering the control volume, Q3 and Q convection are going out of the control volume, therefore Q1 plus Q2 minus Q3 minus Q convection equal to 0. Correct? Now you can write for Q1, Q1 is any problem? Which one? I am not making any mistake. What is? This flux is based on this distance only, no? There is no problem. What is the problem? I am evaluating the flux here, it is halfway. So it is this minus this divided by full distance is delta x, na? So the other one is into divided by delta y multiplied by delta x by 2. What about Q3 plus minus H into Tp minus E infinity, that will be positive, is equal to, very good, that is all. Now I leave it as an exercise to you, you can collect all the terms, you can write an expression for, therefore Tp equal to okay, let delta x be equal to delta y. Shall we write it? Shall we spend 2 minutes and finish it? Okay. Cancel out the delta x delta y. Is it okay? okay. Minus h is minus or plus, is that correct? Is that correct? I have taken care of everything, okay. There is a TP coming here, na? Okay. So, what do we do now? 2 TP two plus it is there, where? Minus, where? No, I am having TP on this side plus 2h, is it 2h? Okay, let us look at this equation. This is the control volume based finite difference formulation for a boundary node where there is a convective heat transfer coefficient. Now please look here, suppose H is 0, that means it is in adiabatic condition, this will vanish, this will vanish, this will become 4 TP, therefore TP will be north plus south plus 2 times west divided by 4, that means it is as though an imaginary node existed on that, the west was repeated here, instead of the east the west is coming twice. So that is why if it is adiabatic you can just extend the domain and make it another half, so that you can use the east plus west plus north plus south by 4, which I told you yesterday in yesterday's class method of superposition. That is image point technique, that is what people call as image point technique. So this H could be, instead of H you can have radiative heat transfer coefficient epsilon sigma T to the power of, but it will become little more involved, the T will be, then you have to linearize the radiation and all that, or you have to take the radiation from the previous iteration and use it, that is called the linearization of the radiation. So once you have interior node, boundary node, now you can formulate any problem as far as, so long as it is steady. Of course this will all become messy if you have spherical and cylindrical spherical coordinate, but the logic is the same. You should be able to sit down with pen and paper, if you want to code yourself this is the way you will start. So you can handle boundary conditions now very easily, you can incorporate adiabatic boundary condition, Dirichlet boundary condition and the third type of boundary condition using this, okay, fine. Now let us close this, let us go to numerical schemes for transient conduction. plain slab, plain wall, whatever. Okay. So, your what is the equation number 5 or 6 or 5. Alpha is the thermal diffusivity, K by rho Cp. Okay. Now we can use a finite difference approximation for this. Ti the general formulation. The formulation is incomplete because I am not telling you now at what time the right side is evaluated. I will answer that question. The superscript P denotes the time interval and I denotes a nodal point. Compared to the last two classes what we have studied, the new thing which enters the time. Okay. So, right side I am not now telling you what at what time step the right side is evaluated. Okay. If RHS is evaluated time step P, then we have an explicit scheme. What does it mean? You start with an initial condition, that means for all x you know the value of temperature. So, that is at t equal to 0 is known. So, you start at t equal to delta t, the first time step. For getting the first solution of the first time step, you need to know the solution at 0. That 0 is available, that is the initial condition available to you. Right side is known, Ti of P is known, therefore you can find out Ti of P plus 1. This Ti is any I, this I can vary from 1 to n. Therefore, you can find out the temperature at all nodal points in the domain at a time interval of P plus 1 if the information is available at P. So, it is explicit because the unknown here is this. The whole formulation is written for finding the temperature at any node I for an time step Pi plus 1. However, if RHS is evaluated at P plus 1, it is implicit. You want Ti P plus 1, Ti P plus 1, Ti plus 1 P plus 1, Ti minus all are there. Therefore, it has to be simultaneously solved at each and every time step. So, that is the implicit scheme. So, you have to use tie diagonal matrix algorithm or something, and each and every time step you have to simultaneously solve. You cannot simply march in time. You take a base solution time t equal to 0 and keep on marching in time by just adding at t plus delta t plus 2 delta t without having to simultaneously solve at each time step. That is the explicit, but implicit left side is unknown, right side is left side unknown, you are writing in terms of putting all whatever you want to solve for is on the left hand side and all the other quantities on the right hand side. In any equation in mathematics, right hand side is known, left hand side is unknown. Unfortunately, when you put the implicit scheme, right hand side also becomes unknown. So, several terms are there. So, I minus 1, I plus 1 all the things we want at p plus 1. Therefore, you have a tridiagonal matrix algorithm which have got only 3 elements in the matrix will be important, then you assemble everything, simultaneously solve at that time step, then go to the next time step and so on. Okay. Now, if you work on this, let us look at the explicit scheme. Okay. So, this alpha delta t by del x square is called the cell or grid Fourier number. Now, you can rewrite this as correct. Yes or no? I just combine the first and third term, put it in brackets, second term I have combined with the term from left hand side. Okay. Now, we can prove from thermodynamic arguments that 1 minus 2 f naught must be greater than 0 required. That is, from thermodynamic arguments you can prove that the coefficient which is multiplying the Ti of P must be positive, otherwise you will get meaning, it violates the second law of thermodynamics, you can prove it mathematically. Therefore, if 1 minus 2 of Fourier number must be greater than or equal to 0, Fourier number must be less than or equal to half. Alpha t by L square is the general Fourier number which is used in unsteady conduction. This is the cell or the grid Fourier number for computations. So, the explicit scheme is not unconditionally stable, it is stable only up to Fourier number less than or equal to half. If it is, if you are setting it to somewhere close to a half, then the errors will not grow, but the solutions may oscillate. Therefore, normally people will keep it Fourier number less than or equal to 0.25 to damp out the oscillations. Studies have shown that if Fourier number is less than or equal to 1/6 or 0.166, you get the least truncation error in a scheme. So, seasoned practitioners of finite difference method will set a Fourier number between 0.1 and 0.15 or 0.15 or 0.1, do not try to go to very close to that 0.5. So, this requirement must be worked out for each of these problems. For your problem it is like this, the coefficient of Ti plus P whatever multiplies that must be greater than 0, from that is where it starts. If you have additional terms like heat generation or there is a fin which is losing heat, then you have to find out how it will work out. Now, I can just in 2 minutes I can show you why it has to be like that. Okay. Now, let us consider a slab where it is initially it is hot, initially it is cold, from the surroundings heat is being applied. So, let us consider 2 nodes, this is I, this is I plus 1, this is I minus 1. Okay. We are starting at a particular time step P. Is the situation clear? That is, these two temperatures are 100, this temperature is 50. Okay. that means heat is flowing into the system. Now I am using the Ti of P plus 1, I want to calculate Ti of P. I am having Fourier number 0.6, what happens to my calculation? Fourier number, so I have 0.6 of 100 plus 100 plus 1 minus 1.2 of 50, correct? Will that be the temperature at Ti at P plus 1? No calci, it can be easily done. What is the temperature now? (110). Is it realistic? The maximum temperature in the problem is 100. From 100 it is getting, it cannot become 110, it cannot become hotter than this. Okay. Now let F naught be 0.4, what happens? T of I plus P plus 1. So Fourier number greater than 0.5 gives meaningless results. You are getting a center temperature which is exceeding the surrounding temperature. 90. But the original physics was these two were hot, this was trying to heat this. It cannot get something, cannot heat to some other thing more than itself. Sun is at 6000 degrees, it cannot heat a body to 7000 degrees centigrade, correct? So it violates the second law. So that is what we say, violates, this is 90. So it is bearable, 90 also is too high, but at least it is less than 100. So Fourier number 0.2, 0.3. So this is a quick proof of the point that Fourier number must be less than or equal to half. So therefore when you do an explicit scheme, be careful. Why students prefer explicit scheme? Explicit scheme is simple to solve. Implicit scheme is difficult, but it is unconditionally stable, but once you solve you get very good solution with implicit. Okay, now you know why the cell Fourier number is very important for transient conduction, alright. Now I have written the explicit scheme, you can also write the scheme for the implicit, and that is the right hand side will all have terms which are got P plus 1, P plus 1, P plus 1, lot of unknowns will be there, therefore it has to be simultaneously solved at each and every time step before we proceed to the next step. We start at time t equal to 0, all solutions are known, initial condition is known. From the initial condition you start marching in time, but at each time the boundary condition should be available. So it is called the initial value boundary problems, IVBP problems, because you have got dt by d tau and also d square t by dx square. So it supports two conditions in x and the initial condition. At all times you should know at x equal to 0 and x equal to L what is the story, with that only you can proceed. Okay. So this brings us to the end of numerical methods in conduction.